Now we will learn how to properly vaporize a liquid sample. To vaporize a sample, one typically uses a vaporizing regulator, also called a vaporizer, which is a pressure-reducing regulator with the capacity to transfer heat to the sample at just the right location. Vaporization consists of a three-stage process. First, the sample enters the vaporizer as a liquid. At this point, the liquid should not be bubbling or boiling. Second, the liquid passes through the regulating orifice in the vaporizer, resulting in a severe and sudden pressure drop, which vaporizes the liquid. At the same time, heat is applied, which enables the vaporized liquid to remain a vapor. Third, the sample, now a gas, exits the vaporizer and travels to the analyzer to be read. Due to the immediate transition to the vapor phase, the composition of the gas is unchanged from that of the liquid, ensuring an accurate reading. In this delicate process, there are many variables or inputs that determine success or failure. There are two main sets of inputs. The first set of inputs concerns the composition of the sample. Depending on the composition of the sample, it will begin to bubble and finish vaporizing at different pressures and temperatures. We'll need to know what these pressures and temperatures are to successfully manage the process. As we can see here, the different bubble point curves are in blue, and dew point curves are in purple. The curves are different from composition to composition. Also note that, the area where mixed phase is present, differs from composition to another. We can say that, the more the sample is dominated by one component and this component is not a heavy one, the smaller the size of mixed phase area, and it is easier to vaporize this sample. In many cases with pure gases, we find that the bubble point and the dew point curves are identical and there is no mixed phase area. These samples are the easiest to vaporize. The more the sample is of many different and heavy components, like in this example, the larger the area of mixed phase sample, and it's harder to vaporize this sample. The second set of inputs concerns settings that you control in your sampling system: pressure, temperature, and flow. Pressure and temperature are controlled at the vaporizer, while flow is controlled downstream at a rotometer, variable area flowmeter, and needle valve. We set these inputs based on what we know about the first set of inputs. Proper vaporization requires a delicate balance of all inputs. We will learn in the next slide step by step how to select the setting and control those parameters to achieve correct vaporization. This figure represents a phase diagram for 20% hexane and pentane. When the sample is above the bubble point, blue line, it's all liquid. We want the sample to be all liquid when it enters the vaporizer. When the mixture is below the dew point, gold line, it's all vapor. The sample must be all vapor when it leaves the vaporizer. Between the bubble point and dew point lines is what we call the no-go zone. This zone is the boiling range of the sample. Here, the mixture is in two phases, part liquid and part vapor. Once a sample falls into the no-go zone, it is fractionated and no longer suitable for analysis. The objective in vaporization is to set the temperature, flow, and pressure so that the sample skips instantly from the liquid side of the no-go zone to the vapor side of the no-go zone. Here is a 4-step process for setting your inputs. First, determine the inlet pressure at your vaporizer. This pressure, which is fixed, is your process pressure, provided your vaporizer is located close to your sample tap. In this figure, that pressure is 4 bar. Second, let's set your inlet temperature, or the temperature of your vaporizer. There are 2 objectives. First, the temperature must be low enough that when the sample enters the vaporizer it is entirely a liquid and isn't bubbling. In the figure, the bubble point at 4 bar is 88 degrees Celsius, but we want to build in a cushion, so let's choose 80 degrees Celsius, a round number far enough away from 88 degrees Celsius to be safe. The second objective is that the temperature must be high enough to contribute to the complete flashing of the sample, ensuring that only vapor leaves the vaporizer. When you vaporize the sample, the temperature drops, in accordance with the laws of energy conservation. The sample temperature must be high enough at the outset so that after the pressure drop, the sample is not in the boiling range or no-go zone. In this figure, the vapor temperature after the pressure drop is 60 degrees Celsius, just on the vapor side of the dew point line. Third, let's set the outlet pressure at the vaporizer. Your objective is to drop the pressure below the gold dew point line. In the figure, the outlet pressure is set to 1.5 bar. If the outlet pressure were any higher in this example, the sample would not vaporize entirely. It would fractionate. Fourth, set your flow. Flow is set downstream at a valve and rotometer, not at the vaporizer. In a sampling system, high vapor flow is desirable because it moves the sample to the analyzer faster. However, high flow can be problematic too, because with high flow, more heat is required to vaporize the sample. In other words, high flow results in a greater drop in temperature at the time of vaporization. In the figure, the purple line illustrates the temperature drop. As flow increases, the purple line angles more sharply to the left. Another variable influencing the temperature drop is the heat transfer capability of the vaporizer. Some vaporizers are constructed in such a way that heat transfers more efficiently to the sample. When the liquid sample converts to a vapor and its temperature drops, it draws heat from the stainless steel surrounding it. The critical question is how efficiently can the vaporizer replace that heat and keep it flowing to the sample. The more heat the sample can draw, the less its temperature drops during vaporization. In some instances, it is possible for the vaporizer to be hot to the touch on the outside but cold at the core inside. That's because the vaporized sample is drawing lots of heat and the vaporizer cannot transfer enough heat to keep up. The best solution in this case is to reduce the flow. In sum, the angle of the purple line is a product of the flow rate and the heat transfer capability of the vaporizer. With a good vaporizer and low flow, the line will become more vertical. Unfortunately, there is no easy way to calculate the location of the purple line, and it is not generated by any known software program. As a result, vaporization involves some approximation. As a rule of thumb, keep the flow rate as low as possible without causing an unacceptable delay in the sample's travel time to the analyzer. It's better to start with a low flow rate and experiment with increasing it than to start with a higher flow rate.